Hello everyone, welcome to Campus X. In the previous videos, we have already seen how can we use threads and processes. We have also seen how can we optimize them using pools. In this video, we will first see the advantage of one over the other, and we'll also see where we use threads and where we use processes. And then we'll see some real world examples. Let us first see the differences between them. So whenever you have some IO bound task, you should use threads. IO bound tasks are those tasks which spend most of their time waiting for IO operations to complete. Whereas whenever you have CPU bound tasks, you should use processes. CPU bound tasks are those tasks which are CPU intensive, which means they spend most of their time using up CPU. Threads share memory of the parent process, right? That is one of the advantages of threads, because it shares memory of the parent process, so any thread can call any global variable of the process, whereas processes do not share memory by default, though we can implement shared memory manually. Threads have a lot lesser creation time, whereas processes have a significantly greater creation time, because they need to be created and they need to be scheduled, so it's a major overhead creating processes. The next and the last point is specific to Python. Threads cannot run on multiple cores due to the global interpreter lock in Python, which is abbreviated as GIL. But processes can run on multiple cores because there is only one GIL per process. The reason threads cannot run on multiple cores is because of the GIL provided by their parent process. So that GIL prevents them from being run on different cores. Let's take an in-depth look at IO and CPU bound tasks. CPU bound tasks are those tasks which spend most of their time using up the CPU. For example, CPU bound tasks can be some heavy image processing operations, whereas IO bound tasks are tasks that spend most of their time waiting for IO requests to complete. Examples of IO bound tasks can be network requests, memory requests, and so on. We should run CPU bound tasks in processes rather than threads, because multiple cores in our CPU can significantly speed up these CPU intensive tasks, which is because multiple processes can run parallelly. Whereas we should run IO bound tasks in threads because they do not use much CPU, and therefore there is no point in taking so much pain of creating different processes. Now let's see some real world examples in Python. So first let us see an example of an IO bound task. So as an example of IO bound task, I have taken network request. So I am hitting this URL which returns me 20 movies. This URL is from the MovieDB and it returns me 20 upcoming movies. It has this page parameter, and personally I know there are 9 pages in this URL. So for every page it returns 20 movies, and our task is to retrieve every page, therefore all the movies. So I have this getMovies function which takes in a page, it hits the URL, waits for the response. After getting the response, I am converting into JSON, of course, and then I'm storing that response in a pandas data frame. I have created the empty data frame here which has these columns: ID, title, overview, and rating. Whenever I get the response, I am storing these in this pandas data frame. Now you might ask why I have used pandas data frame here. Pandas data frame gives us a suitable function which lets us store the data in a CSV format very easily. So in this format, in comma separated values. So here I have the ID, the title, overview, and the rating at last. Therefore I have used pandas data frame. So this is the function which retrieves a page of movies. Now our task is to retrieve all the pages. Here I have noted the start time first, then I have made a pages list which starts from 1 to 9. Actually it goes from 1 to 8. I have left the 9th page for now. Our task is to fetch all the pages, and then we are printing out how many movies we got by printing out the length of the data frame. And then I am storing that data frame in a CSV file using the toCSV function, I'm storing it in movies.csv. I have already done that before, you can see. At last I'm storing the end time, and I'm showing out how much time this main thread took. So let's start by calling all the pages. First I'll do it sequentially to show you how much time it will take. So here I'll write for page in pages. What I'll do is get movies with the page. And that's it. I have done a sequential network request which fetches all the pages one by one. Let's see how much time it takes. So in total it took 3.5 seconds and it returned us 150 movies. Now let's apply threading. As you know that this is an IO bound operation. This network request is not doing much while waiting for the request to complete. So we can use threads because they are much lighter than processes. So let's use thread pool executors here. So first of all, let's go up and from concurrent futures dot futures import thread pool executor because they are more efficient than normal threads. I will let's comment out this because you can see that later. With thread pool executor as executor. Okay, when I explained thread pool executor in the second video, I said that there is a max worker parameter that you can change. So you can have 10 threads running, but I did not tell the default value of the max workers. The default value is actually the number of cores that you have in your CPU plus 4. So in this computer I have 4 cores, so the default value is 8. I'm going to leave that default value to 8 just for now. And then what I'll do, I will use the map method of the executor to map all the get movies function with the page. So I'll do executor dot map. I'll pass in the reference of the function that I want to run in a different thread, which is the get movies, and I will pass the pages list. So one more time, what this map does is it calls get movies in a different thread with every element of the pages list actually. Now let's see what happens. Well, it hit all the pages, but it returned us only 41 movies. It completed that operation in 1.5 seconds, which is significantly faster than the previous sequential method. But what happened here? Why didn't we get all the movies? Well, it appears that we get the same synchronization issue, that when multiple threads try to append to this data frame, we lose some of them. So we have to have a lock here. So let's here make an object of the lock class that is provided by the threading module. Threading. Okay, I did not import the threading module, so let's go ahead and import threading. And now I will write threading.lock to make a lock class. And then what we will do is pass in the lock. So for this get movies, to run this get movies, we need to pass in the lock. So here I will have the lock. Before doing every update, I'll do a lock.acquire. And after doing all the updates, I'll do lock.release. So this is just synchronizing the updates to this the data frame actually. And what I have to do is now pass in the lock. But you cannot just pass in the lock like this. This map method requires an iterable to be passed. This pages is a list. And what we have to do is pass in a list of locks, which the length of the page the length of the list of locks should be the length of the pages. But you cannot make different instances of the lock class. You have to have the same lock object. So here what I'm going to do, I'm going to make a list of the same instance multiplied by the length of the pages list. So here what I have done is I am creating a list containing the same instance of the lock class and how many times the length of the pages. So now if I run this, it asked for all the network requests and fetched out 150 movies and it took only 1.24 seconds. So that significantly speeded up our process, and this speed up will be more significant when you have more number of pages or more number of requests. Now let us see an example of a CPU bound task. So here I have some function which mimics some CPU intensive task. It just basically takes a number and it runs a for loop from 0 to that number and sums up the square of the number and returns the sum. I'm just mimicking a CPU intensive task. So in the main module, of course, you have to remember while using processes, we are going to use processes, and you have to use name equal to main when you are in Windows. Then I am noting that the start time, I have numbers from range 0 to 10,000, and let's make it 1000 for now. I will remove that. Here my task is to perform this CPU intensive task with all the numbers in this list. Now at the end I am noting down the end time, and at last I am printing out how much time this main process took. So let's do it sequentially first. Let's see how much time it takes. So for number in numbers, I'm going to apply CPU intensive task with a particular number, and let's note down how much time it takes to complete. So it took 0.34 seconds. Actually, I think it will be pretty difficult for me to simulate these small differences in time. So let me just go back to 10,000. I guess I did it for some reason, and I'll run it again. So you can see it took 18.2 seconds here. So now what we can do is change this sequential execution into a multi-processing execution. So since this is a CPU intensive task, it becomes pretty reasonable to run these CPU intensive tasks in different processes rather than threads. So I'm just going to comment this out so that you can take a look later. So I'm going to use process pool executors here. So with process pool executor as executor, what I'm doing here, I'm going to use the map method to map these numbers with this CPU intensive task. Executor dot map. I'll pass in the reference of the CPU intensive task, and I'll pass in the numbers list, and that's it. Let's run this. Now you have to remember that these processes take a little time to spool up and get created and scheduled. So the creation time is a little greater, but here you can see that this using multiprocessing you took only 15.5 seconds, whereas in sequential execution it was only 18 seconds. And this difference becomes significant when you increase the range. I'm not going to show you this because it takes a lot more time, but I'm going to leave you with these real world examples, because these examples clearly depict where you should use threads and where you should use processes, what is the difference between them, and what is the advantage of one over the other. So thank you very much for watching.